Okay.
So I need to go, Garnet. Thank you very much. I'll be getting in touch.
Oh, you're welcome. Nice to almost see you, Nicola.
Oh, right. Yeah. No, hang on, just a tick. This went over. That's right. Hi. So, yeah. So I'll be getting in touch definitely. Okay. Lots of love.
Okay, great.
Okay. Bye now. Bye, everybody. God bless.
Cheerio, Nicola. Garnet, thanks very much for that. That was beautiful to see how you constructed those, how you reconstructed quantum mechanics from relativity. I have a set of questions and I have a set of comments on this thing, and I think I can answer some of your questions from the physics. So I think we together can take things forwards on this one. So I'd like to do that in a minute, but first I'd like to request if anybody else has any questions or comments. I'll just start the ball rolling then. First, it's a very beautiful step forward you've taken in looking at these things as aerial forms, as momentum forms. In any path in quantum mechanics, you really only have 2 points, and that's the point of emission and the point of absorption. Between those 2 points, all paths are equivalent within the light cone. Now, several comments. The first one is, you've gone to Tor, you've gone to the proper time in terms of looking at square root t squared minus x squared. Now, remember, in those situations, one's thinking of something where everything happens, where every length in that thing is 0 on the light cone. So your t squareds minus x squareds are all 0. And that's as it should be. And you've got the proper transformation of the clocks as well. So what you're seeing in slide 22, when you have a look at equal ticks and tocks going backwards and forwards in space-time, is you're looking at a light clock. You've constructed a light clock, a light in a box clock. And that's beautiful and pretty much as things work. But if we want to look down inside what's happening just there, then the mathematics of that is also very beautiful. And you're right, that the sigma matrices are a better option than using I, but there's a better option still. And if you have a look, and it's available in the Quisical folder, the sigma matrices are actually a subalgebra of the 4-dimensional Clifford-Dirac algebra. And that construction is in there, and that decomposition is in there, and in the appendix that we've put up onto Quisical. So have a look at that, and then you get to the 4D commutation relations of the full Dirac algebra without the square root of -1 getting in the way, which is a 2-dimensional rotation there. And
absolutely, John. Yeah. And you can see from this actually why that works, because the stretch factor and the boost in the Dirac equation, it only happens in the time-like plane between the origin and the final point. So you're right. The whole thing goes over to a 4D in a shot. Whereas when you think about it as a path, everyone's been sort of thinking about the chessboard model, going, yeah, right, don't.
Not a path. It's all paths. Yeah, no, you're right. Just don't. Just delete that from your mind, because it's confusing you. It's confusing everybody, and it's beautiful how you brought that out. I love that. I love what you've done there. That's gorgeous. But another comment: you've got these 4 colors going around a loop, and looking with 2 observers. What's happening with that is any light transformation is outside the light cone when it's moving away from you. So it's not in your world. So if you're looking at the box from one side, you see just the ticks. And if you're looking at the light box from the other side, you see just the tocks. So that's the binary thing that you have there. But the binary thing is no longer tick tock, tick tock, tick tock. It's tick tock, tick tock, tick. Or the other way, it can be tick tock to the other observer, coming closer. And so the thing has a clock, and it has an inner clock. But at the root of all of this, those areas are also uncertain areas. You're looking at something which has a built-in uncertainty with it. Now, the reason for that is that if you look at the action of this, so if we take the clock down, we can abstract the clock as being a tick and a tock. Now, what that is that's light speed away from you and light speed towards you, tick, tock. So you've got the light speed going both ways. But if you want to look at that now in terms of a continuum in physics, so we're looking at the thing in terms of a continuum where we have an underlying oscillation which is responsible for that, then that underlying oscillation is governed by a set of actions. This is actions in the mathematical sense. So actions in this sense are things like energy times time or momentum times position. But if you take, let's say, for example, the energy time thing, the delta E delta T is related to h bar over 2 in the uncertainty relations. But really, E isn't. This is not two different things, because E is really frequency. E is the energy is given by Planck's constant times frequency. So what you've really got underlying these things is properly uncertainty between time and its inverse. And one's talking about inversions here. That thing is the thing which is governing the rate of change of phase, and the underlying thing which is generating the clock. So your clock is determined by a phase thing. It's a light clock. So if your light has a perfect, in the rest frame, your light has a very nice sine. If you like, it has an oscillation that's fitting inside the box. In any moving frame with respect to that, it's going to be deformed by the relativistic transformations to give you these changes. But the rate of change of phase is governed by the action in any frame, ET, for example. But that action is a relationship of inversions. And that process of inversion is your tick. For what you have there, it's your change from one to the other. So that's governed by an inversion, and inversions also govern interactions, and the interactions are what's happening at the point of the emitter and the observer. So all of this stuff fits together perfectly, not by accident, but because, and you beautifully derived this and shown where people are really going on in the Dirac equation, because Dirac made a couple of mistakes in the equation, and and those mistakes have to do with the way that he treats the square root of -1. He brings it in two different ways. And he doesn't bring it in as he should, as being something more like the sigma matrices or like the Clifford-Dirac matrices, for which that's a subalgebra. Now, those rotation matrices, and they really are rotation matrices, the Pauli matrices in space-time space, are what's really governing what's going on. And I love your animation. That's just exactly what must be happening. And you've got both the forward in time stuff, which is the stuff that you see, and you've got the backward in time part of it, which is the stuff that you don't see. Okay, but what you don't see, somebody else does see, because depending on which perspective you have on that thing, it's not that it's gone, it still has to be there as part of the complete oscillation. So in the physical sense, this is spot on. And if you have a look at Martin's paper, for me anyway, I love what you just did. But if you have a look at Martin's paper, the 2019 paper, which is up on Quisicle as well, that's going through the mathematics of some of this as well in terms of the continuous transformation of this. Now, that continuous transformation in Martin's paper generates the de Broglie wavelength from the wavelength of the light that's in a box. You get a de Broglie wavelength. And that's exactly where relativity led to quantum mechanics in de Broglie's mind, because it was de Broglie looking at that back in his thesis, which gave him the lambda is h over p, which is what you insert into classical mechanics to get the wave mechanics. So this brings it full circle. What you've done brings it full circle back to that point where it entered into quantum mechanics. That's the derivation of quantum mechanics before quantum mechanics, 1923. So that's a beautiful piece of work, and it fits in very beautifully with the physics models that Martin and I have been looking at for the last 5 or so years. So if you have a look at those, and also the mathematics, that sort of hierarchy of mathematics between I and the sigmas, and then what I call the alpha matrices, the Dirac, well, they're one of the two Dirac gamma matrices. It's a Dirac algebra. Are well, very beautiful. And as soon as you get to the Dirac algebra, you've got that huge amount of beauty. Although Dirac did, I think Dirac's equation is beautiful enough, because I think it's a bit ugly in one respect, and that's in the respect where he brought mass in. First of all, he got the wrong factor for the mass. He's got the wrong matrix for the mass in terms of the physics of it. And secondly, he's put in a lump of mass, which is not connected to anything else. It's just whoop, drop some mass in there. That's ugly. Apart from that, it's very beautiful, but that bit's a bit ugly. So, but I'd love to talk some more about this. I wish we had a proper meeting here where we could sit down and talk to each other. But we will get that in the future. But very nice indeed, and fitting in with Lou's talk. I think that fits in very nicely with what Lou was talking about, because he's talking about inversions as well in terms of looking at these things. I think inversions are the key. So that's mostly comments. There's not much of a question in there, I'm afraid. So mostly comments there. But I'll shut up now and let other people ask certain things. But thank you for that.
Perhaps just one comment on the comment. So at some point you have to ask, well, where the heck did the uncertainty principle come from? And the thing is, you can see where it comes from in all of this, in the sense that if you're stuck in Minkowski space and you have a continuous world line, then it's like the continuous world line has a signal which is a constant function. And if you have, so all it does is it's either on or off, right? You model it with a delta function. And if you have that, you can actually, in a sense, violate the uncertainty principle because there's no signal. As soon as you put in a signal, then you're completely constrained. You can't get around the Fourier uncertainty principle, right? Because that's an object in the sense that exists in mathematics, right? And it's a matter of consistency. As soon as that goes in, the uncertainty principle comes. So all you have to do is to back away from the continuity of the world line in the Minkowski prescription, and all of this stuff just falls out.
You're right, absolutely. The uncertainty relation is something that's widely misunderstood. Engineers laugh at physicists because it's, for them it's just a consequence of a Fourier transform. The fact that the uncertainty principle really only operates if it's the only thing you know. If you make one measurement and you know nothing else about it, then you have an uncertainty. But if you look standing in the waves in the surf of the sea, and you can see what's coming in as waves, then you can see the wave. You know the wave is there. You've made a measurement of those waves in your mind, and you can imagine those waves coming in continuously. Even though if all you knew was the height of the wave, and its momentum, if that's all you knew about it, which isn't all you know about it when you're looking at waves, you know a lot more. And I'm hoping to get a friend of mine to give a talk at Quisicle. Haven't persuaded him yet. He's shy. To show how music, in terms of music, he's just had one of his students finish a PhD on looking at the limits of the uncertainty relation in terms of musicality, in terms of what you can know more about position momentum in terms of the music. And I wanted to talk about it. It's absolutely beautiful and instructive. Actually,
that would fit in with this, because when you look at where the de Broglie wavelength comes from the Dirac picture, it's the beat frequency superimposed. Think those. You can look at the zigzag picture as being two spirals that as you increase the momentum, you have, as you pointed out, instead of tick tock, you have tick tock, tick tock, tick tock, tick. And the de Broglie frequency is actually just a beat frequency sitting on the top of those. So
that's exactly what Martin derived back in 1991 as one of the first things. Nearly made me fall over. But it's also exactly what de Broglie derived back in 1923. So I think there's priority there. We'll give this one to de Broglie. We thought we had something beautiful there when Martin derived it for the first time. It was a few years later that we were pointed out that we were sort of preceded by somebody who was a bit smarter than both of us put together. So there we go. Lovely to see. But yes, it's exactly that. So you have these two spirals, and the spirals are kind of connected. Imagine two spirals with a bead connecting them. And so as a spiral goes past you, that's like wavelength happening. But if they're connected by a bead, if you move one and not the other, or move them both, they can move at different speeds, and the bead still connects them. So the harmony of phases, which is at root, the relativistic root of quantum mechanics, is that it is that there exist two oscillations, one which speeds up, one which slows down, in such a way that they remain in phase with one another. And speeding up and slowing down gives you a beat, and that beat is the de Broglie wavelength, and that's how de Broglie derived it. So a slightly better, not much better, because it was pretty much perfect to begin with, description of that is in the 2019 paper by Martin, if you want to have a look at it, because that just does the more general case of light in a box in all possible directions. So, and it shows that the Doppler shift doesn't just work with two things going through one another, but it also works sideways as well. So, and you get the de Broglie wavelength, all possible directions in which light is traveling in that paper. So it's a nice little bit of work, that, and fun to look at. Okay, I'm going to turn off my mic again. Any more, though?
I have a question. If you think of Dirac's original insight as starting with E² equals P² plus M², and replacing it by E is equal to alpha P plus beta M, where alpha and beta are some algebraic elements, and then going from there, how do you see that shift in your terms?
Well, how to put this? He's not an inspired guess. Well, to say he's an inspired guesser is somehow derogatory, which of course he wasn't. This has, in a sense, to do with mathematical intuition and sort of how these things work. I mean, when you, for example, compare that to the chessboard model and taking this thing to 4D, it's along the lines. So it's along the line of Minkowski. His first guess was to say somehow replace T by I times T, and the I gives the T a period 4 frequency in a sense. And when Dirac came to it, I mean, I think this is why it's always called a rabbit out of a hat, because you have to sort of, he was looking at the mathematics and saying, well, how the heck do we make this stuff work? And I guess he just learned matrix algebra and thought, well, supposing we try this. And I think what happened historically is he tried that, the damn thing worked, and so at that point he had to figure out, well, what does it mean? And it's harder to figure out what it means than taking sort of the applied math approach to saying, you know, what is our understanding of how this could possibly work?
Well, one possibility for interrelating it with the way you're thinking is to think of the Clifford algebra as interpreted temporally, just as we've interpreted I temporally.
Yes.
And then to look at that. It's worth thinking about.
Well, absolutely. I mean, Lou, I was going to ask you. I mean, sort of following what you've been doing. I mean, you've clearly seen the idea of the binary expansion, that you can go just about everywhere, and so this picture. I mean, in your formulation, you've also got Maxwell's equations, and so my guess, one guess in the question. One guess is that by employing your ideas directly from discrete physics, which is really focusing on the switch. So for you, the iteration is all about the switch. And so in the end, you can talk about points because the switches, in a sense, are points. So can you do this to get Maxwell's equations, which I'm pretty sure you should be able to do. And B, of course, your interest in Spencer Brown stuff. If you're going to, since you know. You can do all this stuff with just a binary choice. The question you have to ask in order to get to binary choice is precisely the one that Spencer Brown was talking about, and the idea of the fact that you've got to make a distinction.
Well, what I mean, Garnet, is the following. Let's take the Clifford algebra, alpha and beta, and I'm just using two-dimensional physics, one dimension of space and one dimension of time. Then you can take the alpha in the alpha p plus beta n. You can take the alpha to be a -1 + 1 matrix, diagonal, -1 and +1 on the diagonal, and the beta to be the permutation matrix. 0110. All right.
Yeah.
So that's this. So they're both temporal. One is the temporal shift operator. That's the beta, and the other one. And the other one is the representative for the switching back and forth between -1 and 1. And then in the alpha and beta individually, they are separated from one another. And when you multiply them together, you get I. I as the temporal entity is the combination of the alternation of -1 and +1 with the switch.
Yes.
So in writing down the Clifford algebra expression, alpha p plus beta m, one is taking the two ways of viewing the time into separate pieces and then creating an algebra out of which they can combine and recombine. But that's still too abstract. I think if we think about it in the way you're talking about it, it's going to become concrete, rotational, geometric, area path kind of.
That's right. You're right. It is too abstract. And if you look at the specific direction in terms of the subalgebra, it is indeed the 1, 0, 0, -1 thing that exists in the two-dimensional part of this, the projection. But what Garnet's been talking about is looking outside that and the diagonal pieces, which you need the full 4D algebra. And in the way that Dirac introduced those introduced the square root of -1, but there's a better way to do that using the signal matrices, which is in the paper. Now, once you start bringing those in, you get a couple of phases coming in. One of the phases is just the Tick-Tock phase, is the one that you talked about in terms of looking backwards and forwards. The other one's like a Berry phase coming in as well, which is also needed for the rotation. So you do need the full 4-dimensional algebra here to really understand what was magnificent about what Dirac did, because really what he's doing is he's looking for a square root of the Klein-Gordon equation, the Dirac equation, and he's found an algebra that implements that. That's his original Dirac algebra. Now we've found a lot more algebras to do that, because the Dirac algebra, of course, is not unique. And the best projection of those in current algebras is the Dirac gamma matrix algebra, which projects onto time, space, better than any of the others. But it remains the comment and the point at which everything went into the mist in terms of Dirac's understanding of what was going on, and Dirac was man enough to admit this as well, even in his textbooks, was the point where he started looking at what should have been the different parts of the Dirac equation, which should have been in there as well, but they weren't in Dirac. They were brought in terms of the vector potential in Dirac, and that's a bit of a mess. It's a bit of a spastic hamburger, the way that's been brought in and is in the standard model. There's a better way to do that, and the better way to do that is to put the Maxwell's equations and not just the minimal coupling in, as is usually done with the Dirac approach. So if you make sure the Dirac equations are in there properly, then the electric and magnetic fields, which come in as areas, fall out separately, and then you can do things in terms of fields instead in terms of spinners, and that's much, much more beautiful. So this is, of course, a work in progress, but looking at the two-dimensional analogy here gets you some of the way, but you do need the full 4D stuff to get the beauty of the square root that Dirac put into this thing. So, but I think that, Garnet, to answer your question about what Dirac was doing, he wasn't just lucky. I think there was a lot of work. There was quite a lot of work over several years looking for that algebra. I think that was a serious amount of try this, try that. What about this? That was a piece of intellectual magnificence of the first order, finding that thing. And I don't think it was in any way, shape, or form luck. I think that was, well, luck that he was born, perhaps. But apart from that, that was very, very smart guy.
Well, so, yeah, of course, he was absolutely brilliant. But I also think he did, as he said, he had as in the sense, I think mathematicians often do, they have a sense of beauty of the mathematics, and you know, his ability to recognize, oh, this stuff actually works, and look how it works, and you've condensed an unholy mess into something that is concise and beautiful, and so he had that sense, he had that aesthetic in space.
And what it must have felt like to do that as well, because me reading it, when I finally understood what he was on about when I finally got what he was doing, that was just such a feeling, just following the man I mean, to actually do that for the first time and to write it down for the first time. And he was so far beyond his peers at that stage, they hadn't a clue what he was on about. But it took a little while for other people, for mere mortals, to catch up with that. So beautiful piece.
He didn't even write it on the side of a bridge.
No, he didn't. Although it took lots of walks in thinking it, that was his inspiration was out in nature.
So the second tier of my question is a little farther out, which is what does your view look like from the point of view of Peter's nilpotence, which is the same question because it's about the Dirac algebra pushed around a little bit differently.
I have the perfect answer to that, Lou. I think we have to ask Peter.
Yes. Well, you see.
No, I mean it's clearly it's thoroughly relevant, and I wish to heck I knew more mathematics. I mean this third wave of tackling the original question that came up with infinitesimal calculus, and people would say, well, you can't use infinitesimals; it doesn't work, right? It's not rigorous. And so you then came along, I think sometime in the '60s with long-standing analysis, right?
Robinson,
Yes.
But the funny thing is that for a long, long time, people were teaching calculus perfectly well using infinitesimals, and all engineers and physicists use them. But there's this continual worry among the mathematicians and logicians about it until finally it gets to be imprimatur of a very well-established logician who can do it right. Yeah. But if you go back to an old calculus book like Sylvanus P. Thompson or Granville, and you'll see they do it right. They just they do it right in a certain kind of intuitive way.
Yes. Yeah. So the thing that I can't remember the name of the third something like smooth. It has nilpotent squares. My brain has forgotten the name, but that
nilpotent calculus. Yeah.
Yes. Yeah.
Absolutely.
So
right.
another a beautiful resolution of the mathematical problem in a sense. But of course, Peter has taken the whole idea to another degree. So I think we should try and lean on him to get him to give a talk about it.
It's not talking.
You're muted, John.
Oh, sorry. Peter, you've got your microphone off as well as me. So we can't hear you.
Can I talk next week?
Would you like to talk next week?
I think I've got a talk I can give next week.
Brilliant. Okay. We have
Decoded.
Send me a title, and if you like a short abstract, I'll post it. Dirac what?
Dirac Decoded.
Brilliant.
Decoded. Okay.
Great.
Decoded, was it?
Decoded.
Decoded.
And if I might be like Garnet, I might need 2 weeks.
Can we put up with that? I don't know. You for 2 weeks. Brilliant. That'll be absolutely fantastic.
But I've been interested in Garnet's work for 20 years or so. So I think I might be able to mention something connected with that. The two paths you have. The what do you call them?
You have to wait until next week. Can't you give it tomorrow?
Oh, Garnet, could you send a copy of your slides by email over to me?
Sure.
Send them to Arnie, and we'll post them on Quasical. Everybody will get them then.
And I'd also like to ask if I can include more people in the audience.
Oh yes, please feel free to invite.
Yeah, we can organise that, can we? Yeah.
If you send me who you recommend, I'll add them to the provided they're willing, of course, add them to the Quasical mailing list. And that's open to everybody, by the way.
So I've got my phone here. Oh, text John.
Am I on at all?
Yes, Lou, you're on.
Oh, okay. I had a couple of questions, more from a physics point of view. does this at all, you know, the square, I love the rotating squares. When does this at all have to do with Schrödinger's Zwitterbewegung?
Oh, yes.
Yeah.
Absolutely. Right. So the Zwitterbewegung arises because if you think of those those paths and the areas that occurred in the slides, they're broken line segments, and they're all at 45 degrees. And when you look at the Dirac model, you actually have these sort of diamond figures. Well, if you think of that in terms of persistence, so you're inside the what amounts to be the Compton wavelength, then when you persist, you actually persist along the light cones to sketch out those squares. And so when you ask the Dirac equation, well, you know, what is my speed? Well, if you ask it in one way, you find the persistence operator, and it just says, okay, well, I'm just heading out along the light cone, and so my speed is plus or minus c. So it's another case of these. You see, it's not mysterious at all in when you think of the analogies in statistical mechanics, where you know in real systems you always have an inner scale, and so in the inner scale in fluid systems, you think of particles. They're just happily going along in their particular direction in a straight line without any accelerations. And so if you ask the same question of a particle that's diffusing, and you ask the question of its velocity on a scale that was below the mean free path, you'd find, oh, well, this thing is moving at about the speed of sound, right? It would fluctuate because it can fluctuate. The same question when you ask the Dirac equation is, well, it can't actually fluctuate. It's stuck at c, because what you're really doing is you're describing these causal areas, and the causal areas have boundaries that are you know, they sit out along the diagonals on a space-time diagram. And so the Dirac equation, if you believe the differential operators completely, and say these things really do go down below the scale of what is really the equivalent of the mean free path, it will pick up the Zwitterbewegung simply because it has to, it has to have that propagation within the areas, right? And it's just looking at the boundary of the areas. So when you ask the question, you always hit the persist, and you never interact with the switch. It's only when you go to longer time scales and longer space scales that you go, oh, well, this thing, you're really now beginning to look at, in a sense, the path on scales greater than the Compton wavelength, and there in a sense the velocity operator becomes a bit more sensible in terms of what one what actually sees macroscopically in particles. Yeah, so the Zwitterbewegung is absolutely there, right? In terms of, in a sense, it's in one way you're asking the wrong question. In another ways, you're asking completely the right question, right? In terms of the velocity operator, there is this mixture that there's in a sense there's a velocity below the scale of the Compton wavelength, and it's always c. And if you ask the question of the velocity on the higher scale, you actually pick up the contribution from the switches, which comes through p.
Yeah, but the switch in the Zwitterbewegung is at twice the Compton frequency. So what you've got both in the Dirac as well. So it's below the scale of the Compton wavelength, sub that. And it's exactly that. It's exactly right. It's exactly as it should be. Yeah.
Now, when you switched from the more abstract to adding P and then delta Q, those two combinations make action. So your equation actually is an e to the I times a action. And does that relate then to the area? In other words, the squares become, if you look at the area of the squares, which you emphasized, is that then, from a physics point of view, related to the action of the switch and persistence combination?
Yes, it does. So maybe one way of thinking about this is if you're on a very fine scale and you're on the scale below the Compton wavelength, then if you look on that scale, what you're really seeing is these inside the area, which is dominated by the fact. Think of it in terms of John's photon clocks, right? At one switch, it's like having two photons being ejected from the origin, and because they're initially diverging, you're creating an area. And if you look inside that, what's dominating is the whole idea of persistence, and so you see something that's quite different than when you're looking on scales that are large compared to the Compton wavelength. When you're looking on scales that are large compared to the Compton wavelength, then you see what we would normally call, in a sense, mechanics. Simply because the P, in a sense, becomes dominant, right? So
it's momentum space you're looking in.
Yes.
And what you're looking at is a circulation in that space. So a visual way of thinking about this is not that it's oscillating at C, but it's going round and round in circles at C.
Yes.
And that's the area. It's inside the circle.
Yes.
Yeah,
So,
and that area then could be a discrete H, right? A Planck's constant kind of area or something like that, huh?
That's exactly what it is.
yes.
Well, half H in this case.
Okay.
Of course, for the distance of it's a half H, but it's an angular momentum, which is a quantized angular momentum.
Yeah.
And in fact, quantization is coming from that continuity of that loop. You can put quantization in just as a number, but that's a very weak way to do it. A better way to do it is to put it in as a boundary condition, which is essentially a circulating a continuous boundary condition around a loop.
Are there any physics? And the reason I'm asking this is because I have a model in which charge mass kind of circulates around very, very similar to what you've done mathematically, but in my model, each of the corners would represent a charge mass charge rotation. Is there any relationship that you can see between the charge mass that we know about in physics?
Can I answer that question? Because experimentally, no. If you start looking inside these systems, you don't see an off-center mass. You see the mass being concentrated in a single point, and that point gets smaller and smaller as you look at it harder and harder. So it doesn't look like a couple of masses or a couple of anythings or four anything going around one another. That rotation that Garnet's been talking about is in momentum space. It's not in space. So we're talking about a space-time rotation, really. He's talking about space-time rotation in a space-time plane, not in a spatial plane. So that's what you're observing currently.
Okay. I'll send you something, and then by the way, Garnet, could you just like last time, could you send me an email on this, because I have older equipment and I don't get all the stuff.
I think there is some connection, actually.
Sure.
Yeah.
What Wolf is saying, I think there is some connection.
I guess maybe another way of looking at this whole thing is if Kronecker was looking at this whole thing that we've looked at, he would stick to his guns and saying, look, guys, this is all about counting a number, right? The continuum limit is all very well, but if you once you're thinking in the continuum limit, it's much harder to go back than to go forward. So Kronecker would say, look, the telegraph equation, the Dirac equation, they're both reflecting symmetries that just sit there in the good old binomial coefficients. So the issue is number, and you don't actually get the physics out until you go, well, okay, this piece over here corresponds to that physical object or process. So my guess is that there are in some ways lots of different ways of looking at what we've already got by the process of saying, well, look, can we find the counting in physics? And I mean, Dirac got there through something quite different, which was some aesthetic sense and a sense of beauty in mathematics. He didn't focus on the idea of a number versus magnitude, which is, you know, what Kronecker and Cantor are arguing about, right? Kronecker is saying it's all in the numbers. If you can count, you can figure out what's going on. And Cantor saying, well, not really, because the real numbers are just too good. Right? They're too good. They represent stuff, even though there's these awkward infinities involved. It represents an image that is useful. So, you know, Cantor's at least Kronecker's perspective will be put away the continuum until absolutely the last minute, and figure out what's going on when you can still count. And then in the last minute, put in the continuum limit to get rid of the awkward details. And that would be safe. So if that's the case, a lot of these models that one is inclined to look at from the perspective of partial differential equations, if you can back up, you can probably come up with different versions of it. So that's my theory.
I think at least from my point of view, the transition from mathematics to physics always involves units. And that's a big question as to what units you want to apply to the counting numbers, and that's where the physics comes in. So,
well, yes.
Anyway, this relationship that you've said, for me at least, does suggest a relationship between space, charge, mass, and what I have in the past promoted is that there is a force between charge and mass, which is kind of hidden in physics, because there is no theory really except the Lorentz force equation that connects charge and mass to each other at all. It's all an assumption that particles are made of charge and mass, or whatever they're made of in the high energy field. So your formulation is very suggestive here, for me at least, that there may be a connection between these two in this formulation. So
great.
I'll have to explore it further and ask better questions. But thank you. It was very. I really like this. So thank you.
So, I think you're right. I think there is one.
Yeah. Well,
yeah.
Peter, I've been wanting to talk to you for a long time because I've got your book. And I'm studying it all the time. So
we have to get together. But there is a connection, and the connection that you can lay in modern physics at the moment is between charge and mass. Is if you're looking at two different perspectives of charge. One of them is the charge from Maxwell's equations, or from the measurement of electric field in macroscopic systems. You have charge as something which generates field. In quantum electrodynamics, you're looking at charge as something which is a mass exchange between particles, an exchange intermediated through photons, but it's mass going from one place to another place. So the connection between mass and charge then is just from two different ways of looking at the nature of charge in terms of classical physics, or in terms of classical electrodynamics, or in terms of quantum electrodynamics. So the nature of charge in those two things is mass exchange in the one and electric field in the other. So, but I can't wait until we get all of us into the same room. And there's a lovely lady in Scotland who's perfectly happy to host us all in the middle of August if the coronavirus evaporates. But I think it's probably going to have to be next year, unfortunately. So we'll get together.
Well, Peter's got this idea that there's mass and then three charges, so that gives you four components. And again, we're talking about four things that in some way have to relate to each other, which have all been worked out. But could fit into the corners. I'm just speculating there, but
if anyone's interested, I gave a talk yesterday to a different group, but we posted it up on YouTube, and that deals partly with what the question you just asked, Wolf, in terms of that set of different possibilities for interaction. If anyone wants to have a look at that, then it's up there.
And what under? Could I look it up under John Quigley?
Well, it's just up on YouTube. There's a YouTube. If you go to quisicle.com, you'll get a link from that. So you just need to.
All right.
Hello,
Thank
Sydney.
you.
Yeah, I just had a quick question. Is Quisicle open to me? The link?
It's open to. I think so, Sydney. I mean, I don't know. I'd have to ask the person. I'd have to ask Mark who set it up. But it should be open to everybody who's on the mailing list. Is everybody getting it? Or if anyone's not getting it, let me know. We'll fix it.
Sydney, do you mean quisicle.com, or do you mean the Quisicle YouTube channel, or the Google folder?
I just meant the folder with some of the things that they're posting on some of the information. If Peter's on the mailing list, that's fine. I can just get it through him.
I think everybody should be able to get hold of this Quisicle folder. If not, something's gone wrong. So everyone on the mailing list, I can email you separately as well, Sydney, if you send me a separate, I can add you in separately if you like.
Oh, okay. Thank you. That's all I wanted to ask.
Yeah.
Okay.
Any more comments or questions?
No.
That's been a wonderful session. Thanks for sharing all that stuff with us, Garnet. That's beautiful. So look forward to Peter's talk, coming back on answering some of those questions next week. So on the next couple of weeks. The other thing is, Peter, when would you like to do it? Because we can equally do it. It's up to you to fix a time that's good for you. It could be Saturday.
On for the moment. I'll stick with this one.
Okay.
I have to have a very minor operation on the Tuesday after. So I presume I'll be all right. But if I'm not, I'll just postpone it for a couple of days after I've had the operation.
Okay, we have other folk lined up as well, so there's plenty of talks coming. We may switch.
What I'm doing would follow so well from what Garnet and Lou have done that it would be ideal to have it now.
I can't wait. Actually, it's a real pleasure to listen to you every time. So, so next week, well, the sooner the better, as far as I'm concerned. So, good. Right.
Okay.
Well, the pleasure awaits next week. Peter's on. Just, I've got Dirac decoded as a title, which is all we need because we're just friends here. We can be. But if you want to say any more than that, doesn't matter. That send me a short abstract. I'll post that to.
I haven't written an abstract, but I could do.
Don't worry about it. The title's enough. We're all going to be there listening to you anyway. So
Okay.
so you can tell us at the point. If it's extra work and you can't be bothered, don't bother. I'll stick it up on Thursday next week. Just the invitation to everybody with that title.
Okay.
Good. Right. Well, cheerio, everyone.
Cheerio.
Catch you same time, same place next
Thanks
week.
a lot.